All right. Hi guys, for everyone who was in the room for the Lolcats talk, I'm very pleased to announce that the audio is now actually working. So, yeah, right? So Ethan won't have to project his voice for the first approximate half of his talk. But it's my pleasure to introduce Ethan Danahy? Danahy. Shoot. Who's going to be talking about how he uses LEGO tools to help teach programming techniques to really little kids so we can indoctrinate the next generation of computer scientists from a young age.
Thank you. All right. Can everyone hear me fine? Okay. I talk loud, so I might not even, I don't want to overpower you. I talk fast too, so get yourself prepared. So thank you to the whole committee and the whole ACM group for having me. This is great. It's been an awesome conference, and it's been fun to see the other talks as well as participate in sort of everything that's going on. So thanks again to you guys. As she said, my name is Ethan Danahy. I'm from Tufts University, which is a university just outside of Boston, Massachusetts. We're about 5,000 undergrads, so it's a small campus, so I'm very overwhelmed being on this one. But it's fun. It's great. It's great to see your facilities and be able to hang out. As she said, I'll be talking about teaching programming through engineering and LEGO Robotics. My title at Tufts is Research Assistant Professor in the Department of Computer Science. And so I want to overemphasize that I am not a LEGO sales rep, although it will probably appear as such throughout the talk, because I'm very passionate about LEGO products and using LEGO products. But that said, I'm not actually technically trying to sell you on any of them. I'm trying to sell you on the ideas. And the tool set that we chose is LEGO, but there's certainly many ways to skin a lolcat, to go about achieving the same sort of objectives. And so while we do LEGO, there's other ways of going about it. But this talk will certainly focus on the LEGO work that we've done, that we've seen being done, and such like that. So in addition to being a research assistant professor, I also work for this, in the Department of Computer Science, I also work for this group called the Center for Engineering Education and Outreach. And so our big goal, our tagline is improving education through engineering. Our goal is not to turn everyone into an engineer, because that would be awful. But rather, we feel everyone can sort of benefit, everyone's education can benefit from a little bit of engineering. Basically, we're trying to get people technology literate. And by doing so, by taking engineering concepts into the pre-college. So typically, you only sort of realize what an engineer is once you get to university. But we're trying to expose fourth graders and younger and older to the concepts of engineering, and computer science being one of those disciplines. So why? This is the why slide. Why do we want to do this? Well, because we're living in this world that's increasingly more and more technology dependent, and you have to be technology literate in order to survive in that. If you're going to be the ones voting on global warming, I would much rather you voting based on some science concepts than on media hype, for instance, and such like that. And so in order to do this, we need to get these kids young, because if you're graduating high school without knowing these sort of basic science concepts, you're not going to be learning it later on. And so getting students excited about math and science and computer science, getting them engaged in sort of learning and being part of this society. And so how do we go about doing that? So we focus a lot on STEM, science, technology, engineering, and math. We do it through hands-on activities, project-based activities. You see where this is going towards the LEGO stuff. We also try to really emphasize this real-world application. So what is the real-world scenario that we can model, that we can replicate inside the classroom, and really make that real-world connection? I know it's from my own schooling, it was always very frustrating to be doing activities where I didn't see the relevance. I didn't see the connection to why you would actually want to do this. And so how can we do that? And as a result, our first goal there of increasing technology literacy, but also we're stimulating creativity, we're getting kids excited, engaged, and also building some of those 21st century soft skills about communication and teamwork and such like that. Okay, so how is the center at Tufts University that I work for, how is it organized? We do research in three main areas. We do it in education engineering education research. So that's really looking at how do students learn, how does a first grader learn different and plan different and design different than a fourth grader or a high schooler or a college level student. We do outreach where we go into classrooms. Of course, you can only sort of hit a 20-mile radius or wherever you can sort of drive to in an afternoon. And so we're also looking at how do we take our outreach efforts where we actually work with students, we go into classrooms, how do we take that, package it up, and distribute it to other universities and other institutions. And then finally, the third category is engineering research, which is what I head up at the center, and that's looking at educational technologies. So my background in computer science, I use that to develop new technologies for assisting the concepts of engineering and teaching and sort of doing those types of things. And out of that comes our products out of our center. And these products are anything from the curriculum and activities, the workshops that we run, or the educational technologies. And so we've lucked out in that these educational technologies that we've developed have actually gotten picked up and distributed by groups like LEGO as actual products. And what that does is feeds back into the system because we get royalties, we get sponsored research agreements, so funds for doing research and such from industry. So what I really want to emphasize throughout the talk, and I'll try to keep coming back to this, is this concept of continuum. It's a word that gets thrown around a lot, especially in education, because how do we get people from point A to point B? Point A being kindergarten up until when they're at the university. And what you want to have that smooth transition between the levels, because otherwise the students become disoriented, disjointed, and they don't follow your train of thought as you're sort of training them in these engineering ideas, technologies, computer science, whatever it might be. And so keep this in mind, sort of this graph of looking at very early elementary through middle, through high, and then up to where you guys are at the university level. And so you'll see, as I describe some of the activities that we do, the projects that we do, you'll see that it really spans this entire continuum. And our goal is try to make that transition as smooth as possible so that the concepts we're teaching you in kindergarten apply to what you're learning in first to second, all the way up through to when you actually go to university. So it's not this sort of drastic change between what I did in high school and what I'm doing in engineering here at college. Okay, so going way back to the very earliest, kindergarten, first, second, LEGO has come out with this product called the We Do set. It was actually sponsored up there in the top left by the top right, by the one laptop per child sort of concept movement. And they said, okay, so if we're getting one laptop for every child, can we also give that child, along with that laptop, a LEGO set that they can actually do not just playing with LEGO, but also doing some engineering. So these are robotic LEGO sets. You can see here this alligator is one of the models that they have where it's connected up to a motor that plugs in and you can actually program it to apparently eat the guy. I don't know. I don't know what concept they're teaching there at the same time. But you can see there's also some other sort of animal and sort of machinery and these types of activities that they develop that are shipped with the product. So we take something like this off-the-shelf kind of product, and we say, how can we now take this into schools, and what can we do with it with the students? There's obviously the activities that come with it, and so what are some activities that we can add to it? So we take our undergraduates who work for us, we took one of our mechanical engineers, and we said, okay, here's the kit, what is it that you can build? And before I say that, let me just say, so there's a whole programming language that goes along with it. Because if you have the student that is making the motors move, making the alligator eat, they have to be able to express themselves in some way. And this actually harps back to what Steve Wolfram was saying yesterday, in that, that's the goal of the programming language, is to try to take the concept that's in the student's mind. They have an idea of what the robot looks like, what the mechanism looks like, and so they build it. But now how do you also, they have an idea of how it moves, how it acts, how do you get them to express those? And so it's through these sort of programming languages like this. We're big fans of the graphical programming languages. There's obviously lots of different ways to go about it, but the beauty of the graphical is that, one, it's cross-language. So no matter what language you speak, if it's English, if it's Russian, if it's German, the program is about the same. It's just pictorial. Second, it's pre-language. So when we're dealing with first, second, and third graders, they're not going to be sitting there writing their C code or their Java code. They relate to these pictures. This is how their brain works. This is what they're sort of thinking as they go along. So anyway, now on to what we challenged one of our undergraduates to do. And so we said, okay, here's the set. Why don't you go and build some things? And these were two of the examples that he came up with. On the left side here, we have a catapult. It's in its lower position, and its upper position, it's hinged by a rubber band, and the student can program when it is that it will actually release. And then on the other side is a crane that lifts and lowers something. So they brought that to me, and I said, wow, that's cool. It's neat stuff. It's fun. But, man, that is some guy engineering right there. Like, let's build a crane and a catapult and such like that. So I said, let's think a little softer, maybe. And how about a flower that reacts to light? And so when the light comes out, the petals open. When it gets dark, the petals close, something like this. And so he went away, and he built this flower here. And so I actually have it here, and I'm going to go try to quickly show you how we actually end up programming it. We program it using this language called WeDo. And so here we are inside the environment. What's amazing about this, and one thing that you won't be able to do sort of with C or Java right out of the box, is this concept of multi-threaded. So it turns out that kids sort of naturally think multi-threaded. You know, one arm's doing this while I'm running, while I'm thinking, while I'm chewing gum, maybe. And so that's how kids think, and they want their robots to sort of react in that exact same way. And so what's neat about this graphical programming language here is that they're actually able to do that. They're able to, just by dragging a brand new start block, they can then control motors with different speeds, having them stop, having them wait, and react to various things. And then you can actually run all three of these things simultaneously. What I'll do is I'll run this guy right here, which is actually now talking down to that model that I've built in front of me. Attached to it is the motor as well as a distance sensor, and that distance sensor measures activity sort of in front of it. So this was the flower, as you'll see, that he came up with. And so when there's movement in front of it, it fell apart. It closes up on it. And so in fact, it wasn't actually a flower. It was oh my gosh, I forgot the name of it. Yeah, Venus flytrap. And I was like, okay, there you go. That's the guy version of a flower, is the Venus flytrap that will eat you if you get close to it. So anyway, sometimes you can't win. Okay. So there we go. And for those of you who can't see it, I'll just run this little video that we took of it where it doesn't fall apart. There you go. So when something comes inside of it, in sight of it, it will close up and eat on it. Okay, so very basic, very simple. Again, we're talking scaffolded. So what we want to be able to do is have a language that allows that sort of very early entry point, so that the first, second grader can get up and running. They can build something, they follow instructions, or they're able to freely build, as well as being able to program it. And so with a limited instruction set, they're able to generate these codes, put them together, and such like that. Our question, though, is how can you take that same sort of tool set and build something more complex? So what's the ceiling on developing these types of things? So it turns out that the WeDo set, due to cost and equipment and sort of all these other constraints, LEGO decided that it should have one motor and it should have one sensor. And so what we challenged one of our undergraduates was build a line follower. Now, if you know anything about line following, the sort of algorithm that you use is here on this side of the screen. And what it is that you start on one side of the line, and while you don't see the line, you turn into it. And when you see the line, you turn away from it, sort of constantly moving forward. And as if the line curves or if it does whatnot, it will follow that line. What this requires, though, is that the motors move independently. Namely, that you have two motors attached to your robot. So one drives it towards the line, and the other sort of drives it away from the line as you're going along. But with this WeDo set, you only have one motor. So it turns out that there's still a solution to that. And so it requires a little bit of tricky programming and a lot of tricky building. But what his solution does here is it drives forward, sort of straight with both wheels going, and the robot will go until it detects the line. When it detects the line, it goes in reverse. But what he put there was a worm gear that actually locks one of the wheels. So it can't go in reverse. It's a slip gear only going in one direction. So at that point, it then, since one wheel is locked and the other is turning backwards, it will actually turn away from the line and then go on repeat. And so he's actually able to achieve a line follower with this set designed for K1 and 2 with only one motor. So what this indicates is really this sort of sliding scale. Again, let's go back to that word continuum of how do you take the same tool set, the same programming, the same whatever, and really apply it to a whole bunch of different levels. So line followers are great. We do them at all ages. We do them with really young. We do them with middle school. This here's my freshman Intro to Engineering course where we use the Mindstorms kit. Here's a line follower that one of the guys wrote. It's the same line follower that they write in 4th grade. Of course, I don't tell them that. But I also make it a little bit harder. So I say, not only do you have to follow that line, but when you're done following that line, I want you to detect when you reach a second line, and then I want you to throw a ball into a bucket. So there you see, you take the same problem, the same line following problem that's pretty well studied and easy, but then you scale it up and you make it more and more difficult. In fact, you can keep going past freshmen to even graduate level courses. So at graduate level courses, using the same LEGO tool set, you're talking controls. And so with controls, you don't want to just do that simple algorithm of turn towards the line, turn away from the line, but you want to do a proportional controller. Hopefully you'll also add in your integral and derivative terms as well, so a full PID controller. And what you can see is that you definitely get a much faster, smoother line follower out of the system. So sort of gives you a sense of how you take the same thing and you can scale it up as you go further and further. And it says Tufts, in case you're wondering. So as I said, that we've had this partnership with LEGO, and so over the last 15 years we've been working for them. About 12 years ago, we released this piece of software called RoboLab. I know some of you may have used the LEGO Mindstorms kits in the past, and this might have been the language that you used. This has been a real coup for us at Tufts, because what happened was that LEGO picked up this product that we were just sort of researching and distributing from an educational research point of view, and they picked it up and made it a real product. What that meant was it got turned into something like 16 languages, 30 countries, a couple of million kids a year using it. I mean, that's pretty awesome. And also, I found it to be extra awesome in that I've leveraged it to actually travel and run workshops and work with educators all over the world. So I've been to Australia and Singapore and all over Europe and such, working with various schools, museums, other educational institutions, distributors and such, in training teachers, working with kids and such like that. Again, it's based on this iconic graphical programming. And taking that further, LEGO then released a follow-up to that called the Mindstorms Nxt software. Similar kind of thing. It's about dragging and dropping blocks. One of the big issues that we've had with this one, issues meaning just not super ideal, is this concept of ceiling. Is that, again, what I'm always looking for is where is that continuum and how do I get from where the product is initially intended to being able to scale up and really be able to address everybody's needs, everybody's desires. And so what we're working on next is working with Labview. That's a National Instruments product. Full-blown Labview is used by industry engineers all over the place. It takes about 6 weeks of training in order to fully know how to use it, which obviously you can't do with a high school classroom. And so our challenge at Tufts right now is researching how can we add scaffolding to a product like Labview in order to get it into high school classrooms, in order so that people out of the box can get up and running, start programming, and be able to start implementing these robotic solutions to the problems that they have. And so that product is, as I said, sort of tied into the LEGO Mindstorms tool set. I have one of the robots right here. And what I was going to do is just show real brief sort of how I envision kids getting up and running with the graphical programming of Labview. So let's see if I can do it in real time. Okay, so the concept of Labview is, again, as I said, is this one of graphical programming. And so you're starting off with your blank screen, and on that you actually drag and drop icons. And these icons sort of represent what it is that I want my robot to do. So for instance, if I drop down a motor icon, a weight icon, and then bring out another motor icon, but set this one to stop, I wire them together to sort of indicate order of precedence, how the program should flow through it. And then the question is, if I hit run, as you can clearly see, oh, there we go. Whew. So there we go. Ran for 3 seconds. I don't know if you can see all the details, but turn it on, go for 3 seconds, and then stop. Okay, that's neat. But again, what more can we do? So let's also read a sensor while we're at it. we'll look at our light sensor. And what I want to do is not just read the light sensor once, but instead I actually want to read it forever. So in graphical programming, what they do is they throw literally a loop around it, a box containing it, saying how long to go for. What I can also do is take that value of the light sensor, throw it out to my to a graph. And then, as I said again, remember, this reads exactly how you would think. I want to be running my motors, and simultaneously, in parallel, I want to be doing this sort of light reading business. And so I can, hopefully, if I run this, there my motors ran for 3 seconds, and then here you can see that I'm continually taking in light values. Yeah, makes sense? Sort of a quick up and going, starting you off kind of thing. Okay. So that's your introduction to Labview. You're all expert programmers now. Yay! Certified, yeah. So in addition to sort of that blank screen, how to get up and running, I mean, that only gets you so far. The problem, and both of the double-edged sword of these programming languages is that you have that control N, you have that blank screen that you start with, and you can do anything you want. But in a classroom, the problem is you can do anything you want. And the students and the teachers both need some scaffolding. They need some sort of information to get them going, some path to be sort of led along, some indication of what I need to do to go from point A to point B. And so that's the other thing that we work on a lot, is sort of developing these activities, these ideas, these code content to get them started. I mean, I know from a computer science point of view, when I started programming, that's what I did. I took other people's code. I didn't start with a blank program and figure out what int main meant from the start. No, I took other people's programs and started modifying it and tweaked it, recompiled it, and saw sort of how it worked and what happened as you ran it. And so we're trying to provide as many sort of code examples shipped with the product that allows that to happen, and really, again, make this smooth transition from previous graphical programming languages up to this one here. Along with sort of what is internally available, we also add these sort of applications along top of it, which is really nice. So the applications allow some more complex functionality. It turns out underneath this is all the same code that is used to run the robot and interact with Labview, but we've put some nice front panels on it. And the front panels that we put, these sort of pictorial interfaces, are the ones that they might find in a lab. So we can sort of simulate scopes or multimeters or whatever it might be along the way. Again, what I want to emphasize is this concept of sort of levels and continuum where you can open up and look inside. And so even if it's a higher level concept, so for instance that turn motor on, you can actually open that up and see what the lower level actions are that actually turn the motors on. So what calls are they making to what ports, what values are being sent out. And so by not hiding sort of everything inside these black boxes, but making the black boxes opaque, I guess, so that you can open them up and sort of get inside. So what's beyond the base sort of Lego where it is now? So the WeDo, as I said, is really targeted to the early elementary. Lego sells the NXT kit to middle school, although we've found a lot of success in, as I said, high school and at the university level. We run undergraduate and graduate courses using this tool set. But the problem that we run into is the concept of this is a toy. And since it is so heavily marketed that way, it's very hard to get sort of into education and convince educators and teachers that it's a real robot and that you can do real robotic stuff with it. And so that's what we're looking at here, is what's that transition? Again, continuum, going from what they know, adding bits and pieces onto it to get them from a toy robot into the real robotics sphere. And so this is Tetrix. It's an add-on to the LEGO product that allows you to do some DC motors, more powerful robotic control with position encoders, and then the metal part, obviously. And what you find is that as much as people want to do this metal robotic stuff, they find that after having done the easy click-together Lego plastic part, that this is a pretty big leap going from one to the other. But you still are able to make these robots that are much more durable and able to achieve some things that you would not be able to do with the plastic bits and pieces. So that was our next sort of question, is beyond just the hardware side of it, what does the software side of it look like? And I'm sure people are familiar with FIRST. It's an after-school robotics program. They have FIRST LEGO League. Some people have been in it. They have FIRST LEGO League, which is purely LEGO. They've now introduced FIRST Tech Challenge, which uses these robots here, these sort of half metal, half plastic robots. And what you do is you control it through a joystick. So I'm a big proponent of autonomous robots, where you program them, you hit go, and it's up to it to have, you have had to have programmed it properly in order for it to go off and do its thing. But they also have the kind that you can control with a joystick. It looks like a PlayStation controller, so it feels very much like a video game. But what's the next step beyond that? How can you still do this sort of controlling it like a video game, but still bring in that math, science, technology, engineering beyond just the sort of video game side of things? And that's what we're looking at here with the intelligent control. This is a product that, again, we developed in our Educational Technologies Lab at Tufts, and is now for sale, distributed through LEGO Education North America to supplement the LEGO product. And what it does here is that as you're driving around, you're going to actually be reading in various sensors. Here we have a light sensor attached, but you could attach any of the standard sensors that come with the LEGO kit. And now you're getting these graph readings. And now what you're challenging the student to do is read graphs, interpret data. What does this graphical representation actually mean about that real world that they're living in? And again, depending on what age and what target you're hitting, you can scale the activity appropriately. But ultimately what we end up doing with this type of thing is, instead of doing that direct visually controlling it with the joystick, is the one student is required to sit with the back to the robot and control it simply looking at this graphical data. So how do you interpret this graph to know what your environment is and solve a maze, find the dark spot in the floor, whatever it might be, just based on the data? And again, reinforcing those types of things. And so then with this metal, with this plastic, how do we take it to the next level? What are the things that you can do with the metal that you can't just do with the plastic? And so we challenged this is a grad student here, but we challenged him to build a car. And so here he built a car that he actually can sit on. Of course, we had to pick our 6'3", 200-pound plus grad student. But anyway, can you actually build something out of Lego, plus this metal Tetrix, that can carry you around? And of course, you're wondering. So I wouldn't be showing the slide if he didn't. But and so indeed, he was able to build this product using Lego controllers. It's the same intelligent brick in the middle. It's the same microprocessor. You know, it might be some stability issues. You probably actually wouldn't want to try to commute to work on this thing, but but it was funny too, because we used a third party. The motors are from a third party, and they were visiting, and so they hadn't seen this, and so we had them actually just drive into the meeting, doing this as if it was sort of like an everyday kind of thing. We put up the parking sign. We made a little spot in the corner. And even they were shocked as to sort of what was possible using their stuff. Okay, so we have some programming, we have some hardware, we have these sort of applications. But how, again, along this continuum, where's the upper bounds? Where can we bring these applications as they get higher and higher? And so here we're actually looking at combining Lego with other products. You saw it with the metal. What does it look like combined with something like the iCreate, right? So this is the iRobots little prototyping device. Actually not in this video, but the other controller actually drives the iCreate. And here we're driving a 3-axis Lego arm, or the Tetrix arm, using a Lego master. Again, it's sort of all using the exact same programming language. So how do you not only have these different processors, these different hardware, the different output, but make sure that the input, what the computer scientist is actually using, is familiar because it's based on the things that they've seen so far. Turns out that programming languages are all about the same. Once you learn one, you can learn the others. And so similar with robotics, robots are all doing sensing, thinking, acting, so reading inputs, processing it, and then moving actuators. So whether it's a Lego sensor and a Lego actuator, or whether it's some other piece of hardware, how do you keep that sort of continuum, that sort of flow between them? In the bottom left here, if you can see it, is a work we've been doing with the Human Factors Department at Tufts, where we're partnering with a medical university who's interested in doing telerobotics in the sense of telemedicine and telesurgery. So you have the big expensive machines where doctors are actually controlling medical devices remotely. Our question was, can we do the same thing in LEGO? So, not, as you might think, so that we can replace the big expensive machines with LEGO. That would be a a political nightmare, but to rather instead to actually bring these education concepts to the masses, right? So within a classroom, you're never going to be using a $20,000 piece of equipment, but you can simulate it using the LEGO stuff. And I think here we have a sort of one of our early trials where we had a master and a slave, so the remote and the local, and sort of controlling it. The actual application that they're looking at here is needle insertion. So if there's any volunteers for that first LEGO medical trial. Okay, so we have some issues with our proportional controllers, and we need to... But again, what you can see is that using the same tool set and the same programming language, you can actually do some pretty complex things. And that's a good thesis right there, a master's thesis in control theory on how to actually start getting these two things talking. And especially when you start scaling it down to the LEGO sort of level hardware, you actually introduce new errors in terms of lag time and latency and communication and processing power that you can't just solve by throwing more technology at it because the technology is already set. And so therefore, you actually have to have sort of more creative engineering to sort of solve these types of things. Okay. Again, we sort of keep just going up the scale. We started with these very simple one-motor type of robots. We move up into the Nxt hardware. This is one of the most powerful ones I've seen, sort of that's at the consumer level. It's called the Surveyor. It's Blackfin ARM processor. You can add on all kinds of attachments. Here in the top left, we have a camera attachment. In the bottom right here, again, it's the same programming language that we've used for the WeDo and for the Mindstorms, LEGO Mindstorms. Now we're just using it at the next level. And so there's that continuum where you can kind of keep using the same thing over and over again. I mentioned camera, and so that sort of brings up this idea of sensors. So what kind of sensors are available? So certainly when you start doing these projects and you start creating these things, you're going to run into upper bounds at some point by the hardware, by the sensors, by whatever it is. And so along with the Mindstorms education kit, there's something like 5 or 6 default sensors, touch sensor, light sensor, ultrasonic, sound sensor, and color sensors, the new one that was shipped. So what can you do with those sorts of things? Do you have a question? And they have built-in encoders, so you can use that as a sensor as well. Exactly, exactly. That's a big step up from the old ones, which did not. So you can actually get some pretty precise control. And actually, that's how those proportional controllers were actually being used, was by reading the motor's location on one and the other. What LEGO has done, it's pretty smart, is start partnering with third parties and making their stuff open source so that others can create sensors that will be attached to it. So, for instance, High Technic is a company out of New York that has developed another, 8 others that go along with it, from acceleration and gyros to IR and magnetic and compass sensors. And then Vernier is a sensor manufacturer out in Oregon that actually has something like 45 different sensors now that can be plugged into the NXT. And so if you really wanted to do a turbidity, go for it, if you know what that is. So, and what's neat about it is that this opens up the possibilities in so many different areas for new things that you can do. For instance, pH sensor. So we've had a school that's actually built a boat, and this LEGO boat paddles itself out into the middle of the lake, drops down the pH sensor, takes a reading, comes back, and then repeats that every day. And so now this class is able to sort of examine over time, over seasons, what does the pH of that lake actually do? Or pond, I guess I should say. Ocean, no. And so then iTechnic also has the prototype board that connects right into the NXT just like any other sensor and can be programmed in the exact same way. What does this allow? Well, actually, this allows anything. So forget the 6 plus 8 plus 40 different sensors I listed before. Now you can build your own, and you can make your own X, Y, and Z, whatever it might be, type sensor. This slide also highlights something else, and it gets back to that concept of Lego is a toy. It is a toy, no doubt about it, but it's also an educational technology. And so what we'll do is we'll start with, on the left there, the same Lego brick that we've seen the whole time. When people say that's a toy, I always want to just pull off the casing and say, how about this one? And they go, oh yeah, look at all those wires and those, that's a real robot. And I'm like, it's the same thing. But this here helps us make that transition, helps move along that continuum. Because what we do is the first year we start with this Lego plastic encased thing. They learn what the basics are. What does input, what does processing, what is output, how do robots work, what are the fundamentals. And then we, instead of attaching the built-in light sensor, we attach this one here and we say, okay, now you're able to build your own sensor. And so now we have the familiar talking with the new as they get into their electric circuits and start doing those types of things. And it turns out that you throw a PIC processor onto this guy here, that's a computer as well. You can program it independently, and then you remove the plastic Lego toy, and you've brought them right along that continuum, right along that path to sort of figuring out the sort of bigger picture and how it all works. And along the way, you're using the same language. You're doing the same computer science aspects of it, the same programming. So I have to include a picture of somebody doing some sort of real electronics, working with circuit boards and wires so that you don't just think it's all plastic. And so that was sort of what Jed was looking at, was sort of how do you move from these plastic into the thing, but make sure that you have a universal language that applies to all of them. So addressing not only the built-in processor that comes with the Mindstorm's brick, but also other platforms. And one of the big ones that's huge right now is the Arduino. And so it's huge because it's super prolific, it's open source, and the big one being that it's super cheap. And so for $30, you can buy your own fully functional, everything included type of board and start getting up and running. And so the question is, can you still use all the knowledge that you had before with this new application? And what you can see is that he's also combining it with some of the old hardware technology that we were using previously as well. Now, this gets into a whole nother area, a little away from comp sci, but I think still pretty interesting. And these are the Makerbots. I don't know if you've seen them or not, but these are desktop prototyping machines. So for under $1,000, I think they're about 700, you can have your own desktop 3D printer. So these are typically reserved for those who have $10,000 or more. Your big lab here, I'm sure, has one or two of the real machines. But here now you can actually do it in your dorm room. Keep your window open. It smells like plastic. And so what you do is you are able to feed in hard plastic. It melts it down, and actually using an AutoCAD drawing, it will print out a 3D plastic model. And so what you can sort of see here right in the middle is somebody making a gear. Now, this thing's not quite at the level of the Lego stuff, so it doesn't mesh completely well, but it's still, you're making your own robots right there. What's also pretty cool about the Makerbots, and a little scary, is that some of the Makerbot parts are made with Makerbots. So yeah, that's robots making robots, and as soon as they're self-aware, we're all screwed. But so what does this look like when we sort of start linking this back to Lego? Well, I can start making my own casings. I can make my own. I'm not limited to the set that I was given, the set of parts, the set of pieces, but I can still take advantage of some of the motors, for instance, here, the power source. You can see peeking out there, one of the Arduino boards actually driving it, connecting up my own homemade sensors way up at the top, or some of the pre-built Lego sensors right in the middle. And so now, again, this is sort of looking at what are the range of options and what's the personal customization that the students, that the teachers, that the classrooms can go through when sort of developing these types of things. And so what I'll jump to now is just talking a little bit about the policy aspect of it. So obviously you see I've been playing with the technologies and the fun stuff, but I also just want to mention this is a report actually coming out of good old ACM in association with the Computer Science Teachers of America, sort of looking at what's the situation of computer science in our K-12 education. And it was kind of grim. So obviously you have your science and your math and your reading and your writing, but where's the comp sci pre-college? And fortunately, there's a lot of languages out there. So I've been promoting sort of the LEGO side of things. But again, you know, there's other ways of going about getting the same sort of thing. So Scratch is up there, Squeak, Logo, of course, from way back. Robot C is sort of the big competitor to all the LEGO default products. LEGO was smart and made the brick open source, so there's actually about 50 different languages that you can use to program it. I actually went on your website and pulled out the University of Illinois enrollment statistics. So if you look at engineering, it's about 16% women. So women in engineering is, of course, another big thing that the study also looked at. They were looking at the K-12 computer science. So what's the female participation in computer science leading up to university? Because how do you get them when they're young, kind of thing? Both everyone in terms of technology literacy, and especially girls with engineering. And it gets back to sort of what I was saying before, was with the activity. The activity that you choose is really critical to sort of hooking and getting people in early. So if you're doing the fastest car in the biggest building and the strongest whatever, you're going to only hit about 50% of the population. But let's work in there's plenty of robotics applications out there that are more open-ended, artistic, and require other skills than just sort of building something that's strong and durable. So. So real quick though, it's not just the activities that you do, but it's also the mentorship. It's having a role model that is there that can do it. And so at Tufts, one of the things that we started was the Student Teacher Outreach Mentorship Program. Again, this is part of our outreach that goes out into classrooms and sort of looks at how can we assist teachers with getting up and started with these projects, but also make sure that the students themselves have good role models. And by using undergraduates, we're able to sort of achieve that. Finally, just a quick couple plugs. LegoEngineering.com is where we throw a lot of our activities, our activity ideas, and all the support that we do with the LEGO product. And then what I wanted to show is just a couple quick examples of sort of that higher end beyond K-12. What do we do sort of at the university level? So Segway, of course, we saw one here today driving around. And so what does that look like with the LEGO product? Yep, you can do it. There's a lot of complex math there, but it's pretty neat how you can actually achieve it. And this actually ends up going off the table, which I'll stop. Insert your Segway joke there. Segway owner joke. So where else at the university level? Well, actually, yesterday I went on a tour of one of your robotics labs upstairs, and here they were using the same LEGO Mindstorms kits to start doing space exploration, space meaning environment exploration. This one here is pretty crazy. You should definitely go online and check it out. Monster Chess. This guy has 32 LEGO NXTs, each controlling a chess piece on this floor-sized whatever it is, 100,000 Lego piece board. And then finally, this is a project out of Switzerland that just totally blew my mind. You'll see the Lego connection in 1 second. But what they did was they had a force sensor. It's a MEMS device, a super small force sensor. They glue a fly to it. The fly tries to fly, and they can measure the force that the fly is going up and down. What they do is it turns out flies don't operate based on inner ear balance like we do, but purely visual. So if you set it up in front of a computer screen, you can put all kinds of patterns in front of it, and that fly thinks it's flying by putting visual stimulus. So you can take that, you can measure it, and you can actually feed that into a robot. On the robot, you actually have a bunch of sensors that then get fed back into the visual display system of the fly. And so you create this feedback loop where actually you have your fly. Here's the fly down inside of its little amphitheater, I guess. It's like the best movie screen ever for flies. Yeah, and they don't pay a lot, but yeah. Well, I guess they do. They pay with their lives. But yeah, so you have the varying stimulus, and so as more movement's coming here, the fly's like, uh-oh, I better get away from that. As it's coming over here, it's trying to fly the other way. Those movements are picked up, tracked by Labview using that. Here's Chauncey. He's holding one of the LEGO robots. It has 2 ultrasonic sensors on it. As he puts his hand in front of it, that stimulus is going into the fly, and you can see, it's hard to tell, but on the screen behind him, the fly is actually reacting to that. And then they should put it down on the ground. There we go. And actually sort of drive it around. Now, the fly is actually driving it around. Exactly. And as you would expect from a fly, it's a little bit erratic and sort of hard to predict what's actually happening. Sometimes it goes towards objects, sometimes it goes away. And it's fun to watch it interact with other... She gets a little freaked out at some moment. Yeah, exactly. Okay, so just to conclude, there's the continuum. I showed you little bits and pieces along the whole way. It's all in there. K through 12, through university, through graduate school, all the way up to high-end flies driving robots. So thank you very much, and I'm happy to take any questions. Briefly, I guess. Sorry, I went long. Oh, I do. Oh, okay. Well, there you go. Excellent. Okay, way in the back. So I didn't mention any prices. But that's a good point. That's a very good point. And that's the one that, especially when you start talking to teachers, that's their first question. Is, okay, I'm already overworked and underfunded, so what am I going to do? How am I going to get this to happen? As I said, the goal with the WeDo, which was for the youngest ages, was to create a kit sort of comparable to the 1 laptop per child. Just as the 1 laptop per child went over budget, so did this. So it's not quite at that level where, it's not the $60 thing that we're sort of looking for. I forget exactly how much this one costs, but it's, again, what you end up doing is you start pairing people up. I think this one's at the $100 range. And so for $1,000, you can get a lot of kits inside your class, pair up students in 2s or 3s, and you can sort of do it. The LEGO Mindstorms kits, unfortunately, that one goes up to about $350 is what it's for retail. So now you're talking for $5,000 if you want, make sure you have some computers in your classroom and kits for every kid. So what's the solution to that? How do you sort of get around that? Well, one is teacher fundraising and sort of putting the onus on the teachers to sort of do that, go out and find their own grants and such. But the other way is that we end up loaning out. And so sort of at higher education institutions like ours, where we are able to get government funding and grants and such like this, we have a repository of about 500 kits that we end up loaning out each year to local school districts, underrepresented, underfunded types of things. So when we're sending our undergraduates doing this outreach, they'll actually probably come with the equipment and sort of do that. But again, it's based on need. So you get some school districts that can afford it, and we'll say, okay, we're adopting engineering into our classroom, we're buying everyone kits, and then you have the other schools that are like, we want to do it, but we don't have the funds. How do we go about it? So it's the sliding scale again. Yeah.
The test that you had, is that students operating autonomously, or is that networked, or is that just motion control and nothing else?
So that one actually is not in the education sphere. That was actually done by a hobbyist, AFAL they call him, adult fan of Lego. What he did was it's all working autonomous. And so you can have either set can be controlled by human or by computer. He has a whole interface set up, I believe in C# that's actually doing the interface part of it, and then it communicates with a Labview backend server that's talking Bluetooth to every one of the bricks. I think I had here, I don't know if my internet connection is still up and running, but sort of gives you a sense of it. So all the pieces are moving sort of independently. So you can see now that because he wants to do a queen sort of sliding out or whatever it is, a bishop sliding out, that all the other pieces had to shift and do it. It's all programmed in there autonomously. It's pretty ridiculous. You can see that the middle of each square is a unique ID tag, so it knows when it gets to a certain location. But yeah. Yeah, getting all 32 bricks to talk simultaneously was probably one of the biggest headaches of it. And just, other questions while that's playing? Yeah. So, I showed the Tetrix, right, which was the big metal stuff that that goes with the Lego product. They're actually very hesitant to even release that as a product because your fingers get caught in that, you're losing those fingers, kind of thing. The Lego stuff, they are very sort of purposefully tolerant of those types of things because they realize that if that kid's Christmas morning who bought it from Toys R Us gets hurt, they're in big trouble. And so the answer is no. The answer is that the tolerances built in are partially because of cost, but also very much on purpose due to liability. So. Yeah.
I'm kind of curious. You talk a lot about.
Right.
And I'm kind of curious, other than obviously the technology, because that is clearly.
Mm-hmm.
Kind of what we see as the biggest jumps in each generation of.
Right. That's a good question. So you worked with the yellow RCX.
I worked with the yellow brick and
Yep.
going all the way back with the one that was on that series.
Okay, wow. Oh yeah, you got some history there. So this one came out and obviously replaced that yellow brick. And there's actually some issues with that. The yellow brick had some advantages that actually aren't present here. And the big one was that we could bring it younger. Because it was the traditional click-together bricks, as opposed to the Technics bricks, which require a lot of very fidelity with your hands, which little kids with their small fingers actually can't do. And so we were able to bring those Mindstorms, those early Mindstorms kits a lot younger than we are able to with this here. So anyway, this isn't answering your question, but that's the not good thing about it. But with this guy here, I mean, it's the more processing power. I mean, we ran into upper limits with the older technology in terms of hardware, in terms of processor speed, in terms of size of memory and such like that. So as you said, as things sort of keep moving on, keep moving forward, that's sort of the big jumps that we see. And accessibility. So because as it becomes more prolific and they manufacture in larger quantities, they're sort of bringing in more technology and more aspects to it that allows more parts added that then expands the range of what can be done. So with the old ones, the sensor set was very limited. There were some people making their third-party sensors, but they were sort of do-it-yourself, hobbyist kind of thing, not off-the-shelf. And to have something like 60 different, this is ridiculous. 60 different, it took them 4 years to do. It's crazy. But to have, 60 different sensors and such like that, I think it really opens it up for the amount of different areas that you can apply it. Okay. What else? Yeah.
So I know you talked a lot about how the technology.
Yep.
In the end, I mean, how are you partnering with other organizations that are focusing more on how to actually bring things to the classroom, how to actually work with and work with them to bring this to the classroom?
Right. Yeah, definitely. So as I sort of said at the beginning, how the center is divided into three sort of main areas where, sorry, just trying to get back here. The educational technologies is my area. That's what I'm most interested in. Is how do I make the next generation of whatever to get in the hands of these people? But we do the education research and we do the outreach as well. And the education research is not only focused on how do students learn, what are gender differences, but also what do teachers need? What do they understand? Because oftentimes your engineering teacher or even your computer science teacher, think about computer science teachers from high school. It's usually the math or science guy that is actually, by the way, also assigned to teach computer science. I know at my high school, currently it's the physics teacher, and he knows nothing about computer science, and I feel okay saying that because it's my dad. But But, you know, it's that kind of thing where they're one chapter ahead in the book kind of thing. And so what can we do to sort of leverage beyond the technologies, but with the teacher professional development, the support network, those types of things. And so we're working on sort of building the communities which help support those types of things. So that's, you know, these types of things, the communities that the teachers can go to get the resources, to get up to speed, to make sure that they understand the sort of latest and greatest. But then the student teacher outreach mentorship program. So the students I'm referencing are college undergrads, and the teachers are that 4th grade teacher. And what we do is we end up pairing them up together. So the undergrads, like you guys, understand engineering, know the technology, can learn what plugs into what and how to debug it. And that teacher who's been teaching 4th grade earth science this whole time is now suddenly assigned to teach robotics, and they're wondering how to go about doing this. So we can provide the support network for them to sort of actually get up and running. What's really cool is we see how the 4th graders, students, get benefit from this. The teachers understand it. They work first year very closely, second year less, third year, now they're sort of on their own, able to do it. But what does the undergraduate get out of it? Well, so we have education researchers sort of examining that. And it turns out that a sophomore mechanical engineer who's studying thermodynamics and then has to explain it to a 4th grader ends up understanding thermodynamics better themselves. And anyone who's sort of TA'd a course can relate to that. When you have to explain it 30 times in a row to students, you sort of internalize it and understand it better at the end of the day. And so this sort of, it's called service learning. It's a whole area of sort of exploration of what do you get by actually doing these hands-on projects, especially in service to sort of other people. So those are some of the ways that we're sort of addressing it. Yeah?
So you do a lot of this kind of outreach stuff. And cool. How much of it matches against the CSC standards?
So computer science is on the border of what we sort of do officially. So because we're sort of the Center for Engineering Education and Outreach, we focus much more sort of on the engineering. Massachusetts added engineering to their state standards, so there's actually some stuff there. And we also look at doing science through engineering. So we have whole sort of curriculum and activity sets based on animals or vibration, sound, waves, these types of things, and learning that through sort of these same materials. So computer science, not so much yet. And actually that's sort of, I'm young in my career, so that's actually sort of the direction that I'm most interested in sort of examining, taking my comp sci background and say, okay, let's not just do programming, but let's do computer science, right? So teaching for loops is one thing, but teaching computer science is another. And so I haven't seen a lot of that, and that's sort of what that big report addresses is, you know, there's a big lack of it. There's a lot of talk, but not a lot of action that sort of matches up with sort of what's actually out there. So. To be determined, I guess. Yeah. Right. And so if you look at the amount that National Instruments, who makes Labview, has pumped into FIRST, you would see that they're definitely into that. So what's that? So we have not worked that much with MATLAB. I would like to see more partnership with that. Our relationship with National Instruments is so strong that it you know, sort of is politically, you have to be careful, but we try to remain agnostic, right? I mean, we're in academia to be in academia and find the best tool. And so what is that best tool? Well, it might change over time, and so we'll sort of figure it out. But so the WeDo platform that I showed, that code, the Mindstorms, the RoboLab, actually all of those are based on Labview. They all have Labview running underneath it. It's just that they put pretty pictures on top of it. And the reason that National Instruments is pumping so much money into this area without a huge financial return, because they're not making the money off of fourth grade teachers like they are off of IBM or sort of whatever else, is because they see that future, that if you get the kids hooked early, then that's what they're going to sort of gravitate to. So if they're thinking graphical programming, then they'll be doing graphical programming later. Again, I'm not a salesman for this, even though it sort of sounds like it. I also understand that there's other things other than graphical programming. I mean, heck, I was comp sci. I did, 20 years of non-graphical programming before sort of switching over. I think it's like you said, it breaks down a lot of barriers and gets people in the door. But let's use it as a stepping stone and make sure that they're aware of all the different options, not just one kind of thing. And so, a for loop is a for loop is a for loop. Whether you learn it first as a graphical for loop or second or vice versa as a text-based one, So, I don't know. Did that sort of get at what you were saying? Anything else? Yeah. Chaos. Yes, exactly. So we call it chaotic learning is exactly sort of the issue. And so that's what some of our outreach and some of our research is trying to address directly. Because that is a very uncomfortable class situation for a teacher that is not used to that type of thing. What we've seen is that with the proper sort of support network and training, a teacher can get very used to that. But when it's not the teacher as sort of the lecturer, teachers that are used to that become very uncomfortable when they are suddenly being asked questions that they haven't heard before and that they aren't prepared to answer. There's a lot of thinking on the feet that they might not be used to. And so that's professional development. That's leading the teachers through. That's why something like this program works, because our undergraduates are used to sort of thinking in that way and can show the teacher that it is possible now you learn how to do it, and then after a couple of years together that the teacher's able to do it sort of on their own. Yep, exactly. Yes. I would argue wholeheartedly that you can. I mean, I believe software is poetry, right? So that there's many different ways to write the same program, and all those different fiddling. I mean, again, that's programming versus comp sci, right? So programming is just getting it to do exactly what you want it to do. Comp sci is tweaking it in such a way that it's more efficient, that it's running smoother, that it's able to do this, that, or the other thing. And again, it's getting people introduced is step one, and that's sort of where we are at all levels, and then sort of moving on to what are those higher level sort of concepts. So we're still trying to solve that first problem, and then I think those other problems will, once everyone's comfortable with just programming, will sort of emerge as to now how do you program well, kind of thing. So. But the one thing I was going to say is that we're acutely aware of the sort of chaotic environment / blank program versus crazy hardware, what's going on problem. And I didn't talk about it here, but one of our other research areas is how do we create software that supports that. So what's neat is that versus a piece of paper, digital curriculum can actually know about what's going on. So you hand out the instruction set on a piece of paper, you're relying on that piece of paper to adapt to every situation possible. But if it's digital curriculum, that software can look down and say, you haven't turned this on, you plugged the motor into the wrong port, you did this wrong, you did that wrong. Here's some suggestions on how you could possibly fix that. Right now, that onus is on the teacher to put out the mini fires around the classroom by running around and sort of addressing all those issues. So can I, as a programmer, take that, solve those programs in software, solve those problems in software, and help actually assist with classroom management and help reduce the chaotic nature of it in that sort of way. So, yeah. So you always, and I'm just going to keep talking unless you stop me. So, okay, cool. So that's a great question, because what is sort of the ideal sort of situation? I'm actually not a believer that one kid, one kit, one computer is ideal. One that costs way more, but I also don't believe that 3 kids is ideal either, because what you end up doing is you have one building, one programming, and one staring out the window. Right? And so I sort of like this idea of pairs of students where they can feed off of each other. If they get stuck, they fix the problem. If you're by yourself, it's too easy to just raise your hand and ask for help from the teacher. And so what you do is you start building, and again, it gets back into these, what are the other skills that they're sort of learning along the way? And it's the skills of collaboration and communication and sort of figuring things out on your own, leveraging your partner, these types of things. So the other thing that I'll mention that we also often get asked, especially with younger grades, is what should we do in terms of gender splitting the groups? So should we do all boy, all girl groups, or should we do boy-girl groups mixed? And we actually suggest split so that it's all boy and all girl groups. And the reason is this, is that what we found is traditionally young kids, when they're assigned a project, you dump out the Lego bricks, you give them a challenge. The guys will immediately grab the bricks and start building, start doing this stuff and without really thinking about it, and then sort of modify it along the way. The girls in the classroom will take a piece of paper and start brainstorming and thinking about it and planning out what they want to do. Okay, now they have their plan, and they turn to go to the bricks, and they're all gone because the guy has created this ridiculous structure that doesn't work, but they've created this ridiculous structure, and motivationally, that sort of just destroys the females. And so we sort of actually encourage sort of split gender groups and due to that. So. But that's a whole research area. It's amazing how many sort of little corners there are to sort of investigate to make sure that we get it so that it works and tweak it. So. Yes? Which do you find more efficient? So, of course, it varies, right? You have guy group, I mean, you know, and of course, we're making huge generalizations right here, which is always troublesome. But what our task is to take all groups and make sure that they learn the engineering process. And so, actually, let's look at researching a problem, developing prototypes, testing them, choosing the best, evaluation, communication, right? That's the sort of the circle. So, you know, I'm avoiding your question, obviously, but you can sort of see, like, let's address each of the problems sort of individually. And what's also interesting is starting to research, when do students start to design? Because actually in first grade, no one designs. They all just grab. It doesn't matter. And then there's this period where they sort of start to separate. And so in first grade, is there such a thing as thinking about it and prototyping and actually doing engineering? Or is it just your attention span is so short that you just go straight to the build? And so we've done studies which have had some really interesting results in terms of, okay, students, you're required to draw, like we force them. Before we even bring out the Lego bricks, you have to draw what your design is going to look like. Okay, now you can go build it. And then let's look back and see, did the drawings match the building at all? And the answer was no, where they might or they might not. But then we say, okay, how about this? We bring out the Lego bricks, and you're only allowed to pick 10 pieces, and you must build whatever it is, a chair, let's say, out of these 10 pieces, some sort of structure. How do they pick those 10 pieces? Do they pick them well? Are they all used in the final design and such like that? And actually, when you put some restrictions, students will start to sort of analyze and actually do some engineering sort of in there, so, independent of gender at that age, so, which is interesting. So. All right, one more.
Okay. So first I've judged at the
Yep.
teams perform the technical, and I always ask in what gender group who did what.
And?
The boys will always answer, we did most of the robot building, and the girls will say we did the research part. And my question is, so what do you think is the future?
No, well, one, I know it won't be around. There'll be something after it, right? There's always something after it. No, it has its own limitations, like anything, and you need to keep adapting it. I mean, the other thing is that the entire kit looks like this. There's not a piece that isn't gray, black, or white. I mean, right there, you're already having some issues in terms of engaging a wide range of people when you have just gray, black, and white pieces kind of thing. And so I think there's definite improvements that can be made. I mean, not that color is going to solve everything, but you know, every example that they ship with it is a ball shooting killer robot kind of thing. So I mean, and that's marketing. That's a marketing side of things. But there's also a ton that can be done hardware-wise and software-wise to sort of improve the product as well. So, and that's what we do as a sort of research. I mean, we leverage our position very, very strongly. We're into research. We're on the front lines, interacting with these classrooms, interacting with these kids. And so we see the faults and the shortcomings all the time. And so because LEGO listens to us, because we've had this big partnership with them, we're always feeding that information back to them to try to influence them and try to make sure the next product is a little bit better than the last one, which is a little bit better, and such like that. Of course, you're going up with a big international company that has a lot of people talking to them and a lot of factors that they have to sort of consider when they do release a product. So, you get some of your wishes, you don't get all of them, but that's how it is. But yeah, it's not the end. There's more coming down the pipeline, I'm sure. And so, cool. Yep. So in education, the big phrase is longitudinal studies, right? Where you actually start tracking people over time and sort of doing these types of things. We're, like everybody, struggling to do it and working on trying to find those things. So what I have is anecdotes instead, right? So instead of the hard data. But anecdotally, yeah, this stuff's awesome. Because what you have is, we have a school system right now that really supports one type of learner, one type of test taker, one type of whatever. And if you're not that type, forget about it. You're not going to do well. You're not going to excel. But that doesn't mean that you're dumb, that you're stupid, that you're not actually smart. And so what this does is it really has highlighted students that aren't sort of traditional learners and allowed them to succeed in classes and demonstrate that they do understand and have the knowledge and are able to sort of succeed in those sort of environments. And so what we found are students that have had trouble paying attention to the handwritten note test, taking, suddenly excel and are able to build and sort of able to be able to do things with this. So that's been the big success. So. Okay, thank you. Yep.